and then we're going to start at 3. So we'll just wait for another minute. Okay, so we're going to just start. Okay. Hello, everyone. Welcome to session 8B. I'm Jaewoong from Seoul National University. Today, we have 4 interesting talks about the compilers and programming languages. And I'm very excited to listen to the talks in our session. So the first speaker is Jianping Zeng, and he's a final year PhD student at Purdue University. And his research interests are compilers and computer architectures with specialty in soft-error resilience and non-volatile memory crash consistency. And he's going to give us a talk about compiler-directed whole system persistence.
Thank you so much for the introduction. So let me get started. So this is Jianping Zeng from Purdue. I'm going to present our paper. It's called CWSP, Compiler-Directed Whole System Persistence. So let's see some background first. As you know, node memory NVN has been commercialized by many vendors such as Intel Optical Memory, and PMAN and Sensor Memory Semantic SD, and MSBN SDT RAM, and Fujitsu RAM. They can be deployed in data centers to achieve high performance due to unique benefits such as high error density, compatible speed at DRAM, and byte usability, and non-latency. To better utilize the benefits of these NVN technologies, Intel PMAN provides 2 modes, memory mode and WLAN mode. In memory mode, DRAM works as a last level cache, and NVN is used as main memory. This is transparent to the programs. Thanks to the high error density, programs sees a huge memory space and therefore achieve high performance. But data in NVN are dead across power failure. Ironically, persistent memory is not persistent at all. On the other hand, in WLAN mode, data in NVN are durable and persistent, but this mode is not transparent, meaning that programmer needs to modify their program source code, leading to programming burden. As a result, both 2 modes do not fully utilize the benefits of NVN technologies. Then, there's a natural question coming up. Can we achieve both high performance and transparency with persistence guaranteed? The answer is yes. Let's see how that is possible. With PMAN memory mode, we already achieve high performance with DRAM as a cache and transparency. Our goal is to equip the entire system with persistence. To achieve that, we just extend the persistence domain up to covering register files, including caches along the way. This is so-called whole system persistence. Here, whole system persistence requires correct power failure recovery. This is so-called crash consistency. To achieve high-performance crash consistency, PriWork DPO uses existing Intel long-temporal data paths collecting L1 data cache to NVN as a persistent path to asynchronously persistent data being stored. That is, for each data merged into L1 data cache, DPO also sends data to NVN through the persistent path so that they can arrive in NVN in program order without using expensive persistent barriers. But persistent paths alone cannot provide whole system persistence. To address this issue, let's see what's the problem here. So in this example, when power is on, processor executes store instruction, writing new data into L1 data cache. We assume the cache hit here. Then the new data is flushed to NVN through the persistent path in the background. Then when power failure happens, all volatile states are lost. Once power comes back, we have no choice but re-execute the program from its beginning. But there's a problem. When processor executes the loading instruction again, it receives incorrect new data from NVN, leading to wrong program outputs and crash inconsistency. We can clearly see from this example, the crash inconsistency is caused by that memory write after read or dependence. To address this issue, PriWork coupler uses battery-backed hardware little buffer to ensure failure atomic stop persistence. Since little buffer size is limited, coupler compiler partitions the program into a series of regions so that the number of stores of each region is not greater than the little buffer size. With that in mind, let's see how coupler achieves crash consistency. When power is on, processor acts to store instruction, running new data into L1 data cache. We assume the cache hit here. Then the new data block is flushed to redo buffer through the processor pass. When power failure happens, the new data is dropped. Once power comes back, coupling runtime can safely resume program execution from the beginning of region 2 because we already dropped the new data. In this way, coupling can achieve crash consistency. But the problem here is that coupling incurs too much performance overhead for multiple memory controllers, since coupling needs to stop persistence at the end of each region. In addition, coupling complex underlying hardware design to deal with potential stability issue. Moreover, coupling requires high energy consumption to just-in-time checkpoint the redo buffer. To avoid expensive hardware support, we propose CWP, compiler-directed whole system persistence with minimal hardware support. As we have seen before, coupling is expensive and incurs high runtime overhead for multiple memory controllers. Another design is so-called whole system persistence that just-in-time checkpoints all volatile states, including register files, cache contents, and DRAM contents to NVM upon impending power failure, leading to significant amount of energy. Another design is so-called replay cache that is designed for energy harvesting system where whole system persistence is alone, but blindly adapting replay cache to several systems incurs a 5x performance slowdown. Even though our design, CWP, is a compiler and architectural design, we perform aggressive optimizations to make performance of our design as close to that ideal whole system persistence as possible. Now let's see how our design works. To deal with memory word dependence, our compiler uses idempotent processing to cut off any program into a series of regions so that there is no memory word dependence in each region, as shown in this example. Also, we repurpose existing Intel write combine buffer as a volatile persistent buffer PB that connects store queue in the core pipeline to NVM, bypassing entire cache hierarchy, including L1 data cache. In this example, we assume the power failure already happened at the end of region 2. When power comes back, we can safely resume program execution from the beginning of region 2 because there is no memory or dependence in region 2. In this way, we can resume program execution from the power failure and achieve crash consistency. But we must deal with potential stability issue. Let's see how it happens. In this example, we assume the store and the load act as the same memory location. When power is on, processor acts to store instruction, running new data into L1 data cache and the PB. Here we assume the cache key here. Then what if the processor pass is blocked? Then the new data block is suddenly dropped on its LC eviction. Here is the DRAM cache. Then when processor executes the load instruction, it reads the incorrect order data instead of the new data just written by store instruction, leading to wrong program outputs and crash inconsistency. We can see from this example, the crash inconsistency is caused by that load instruction reading all the detailed data from NVM. To address this issue, prior approaches need to search PB for every single load instruction by including PB as part of cache coherence domain, or using expensive Bloom filter. Now let's see how we address this issue with negligible hardware overhead. We found out we can eliminate stability issue by enforcing the order between store and the load instruction. To achieve that, we just simply delayed L1 data cache eviction until the corresponding data in PB is flushed to NVM through the processor pass. Then it doesn't matter, the new data block is suddenly dropped on its LC eviction. This is because when processor executes the load instruction, it reads the correct new data from NVM. The beauty of this approach is that such order enforcements practically increase low runtime overhead because the processor pass is faster than the regular data pass. Here is the cache architecture. So far, our design achieves high performance crash consistency for single memory controller, but it's challenging to achieve that for multiple memory controllers. This is because of Luma effects of multiple memory controllers. Let's see how it happens. In this example, we assume store 1 in region 1 targets a file memory controller, while store 2 in region 2 targets a new memory controller. When poll is on, store 2 could arrive in MVN before store 1. Then, when poll failure happens, store 1 is lost. Once poll comes back, we need to go back to the beginning of region 1 to resume program execution because region 1's persistence is not completed yet. But the problem here is that when processor executes the load instruction, it reads incorrect new data from MVN, leading to wrong program outputs and crash inconsistency. The crux of the problem here is that store persists all of region order if they target different memory controllers. The one simple way to deal with the issue is to stop store persistence at the end of each region until all price stores are already persisting in MVN like Capri. But this live approach incurs high runtime overhead. Now let's see how we achieve high performance for multiple memory controllers. We found out that there's no harm to persist the store's auto-region order if there's no power failure. Given real power failure in data centers, we propose memory controller speculation that speculates no power failure in the all these unpersistent region and continues persisting stores of the following regions with their data unlocked. Let's see how memory controller speculation works. In this example, we assume the first region is the all these unpersistent region, while second region is under speculation. When power is on, here also, the store 1 is on the way to MVN. When power is on, processor closes the region boundary and speculatively persists store 2 and store 3 with their data unlocked in MVN. Then, after store 1 arrives in MVN, region 1 becomes persisted because all its stores are already persisted. So this is the point. Region 2 becomes the all different and persist region. That indicates we can safely deallocate store 2 and store 3's unlock because any potential power failure in region 2 can be recovered by its execution from its beginning. Now let's see how to recover program states from power failure with memory controller speculation. This figure shows the same example, but store 1 is on the way to MVN, and the store 2 and the store 3 are already speculatively persist in MVN with their data unlocked. When power failure happens, store 1 is lost. Once power comes back, the first thing here is that we reverse store 2 and the store 3 using their unlocks. Then it's safe to go back to the beginning of region 1 to resume program execution. In this way, we achieve high performance crash consistency for multiple memory controllers. Now, let's see the evaluation and the performance numbers. We implement our hardware technique and the compiler technique on top of Gen5 simulator and the L11 compiler. We compare our design against the state-of-the-art Capri for total 6 benchmark suites. This figure shows the normalized runtime overhead of 2 designs compared to the baseline. Here the baseline is running original applications on top of PMM mode without crash consistency support. Thanks to the asynchronous store persistence and memory controller speculation, our design incurs only 6% runtime overhead on average, while Capri incurs 26% runtime overhead on average. In conclusion, our design is the first lightweight is high performance, crash consistency, and persistency for all kinds of programs with compiler and architectural design. We reduce the hardware complexity to the minimal value and eliminate expensive just-in-time checkpointing. This is particularly important for many applications such as machine learning applications, HPC programs, and email databases because we can reduce their expensive global checkpointing. This is all for my talk. Thank you so much for listening, and happy to take any questions.
Hello, Reza Azimi from Huawei. This might not be specific to your technique, but are you sensitive to context switches within regions?
So are you mean whether our design will be affected by context switching in terms of performance?
No, correctness or like crash consistency.
Oh, yeah, this is a good question. We solve this problem because we manually partition context switching related assembly code by inserting region boundary and checkpoints so that Even though the power failure happens during context switching, we can recover program states. Yeah.
Okay.
Yeah, thank you.
Okay, thanks.
Hi, I'm Yuan. I'm from UC I'm wondering the compiler should only be able to capture the program behavior within user space applications, right? So if the program what about from, for example, page table that is kernel mode, and if the kernel the address mapping is being messed up, it's able to fully recover?
So are you asking whether it's recoverable if the page table is corrupted?
Yeah, sort of. Yeah.
It's corrupted by power failure or something else?
Yeah, power failure, for example. Yeah.
Yes, our design can recover program states from that situation because our compiler is successfully to recompile everything, including Linux kernel.
Oh, I see.
Yeah.
Thank you.
Yeah, thank you.
Okay, let's thank the speaker again. Okay, so next speaker is software. Can you actually drop your?
Can I show
okay.
this?
It's on the screen.
Okay. Thanks for the introduction. Today I present one of our recent works that's called Memento, which is a register file cache for modern GPUs. Register file in GPUs requires a very large capacity and high bandwidth, and we prefer for that to consume low energy also. But this is very challenging to deal with, even in the modern state-of-the-art GPUs. Take for example a V100 GPU. It contains a register file that occupies 55% of on-chip storage, and it consumes 30% of dynamic energy. One solution for this problem is that implementing an efficient register file cache. There are many proposals in the literature about implementing the register file cache in GPUs. Some of them propose implementing that independently. However, when you apply these techniques to modern GPUs that support subcore-based architectures, they lose performance. There's also one state-of-the-art proposal called BO, which suggests implementing the register file cache within the operand collector units. We found out that this design is not that cost-effective to support Tensor Core instructions. But why implementing the register file cache, implementing the register file cache independently lose performance? Basically, these designs propose that let's include the register file cache outside the operand collector units and create some routing networks between the banks, the operand collector units, and the register file cache. But since the overhead of doing this is high, they propose let's include a two-level scheduler in which the warps in the SM are split to two sets. One set is active warps, and the other is pendings. And they only issue instructions from the ones that are in the active set and allocate the cache space also for the ones that are in the active set. When a warp gets deactivated, you have to flush the cache, do some extra steps to not lose any data, and allocate the cache to a new warp. However, if you apply this technique in a subcore-based architecture, it loses performance because in the subcore-based architecture, resources are partitioned between the subcores, and now the two-level schedulers manage fewer warps, and even fewer of them are active. These few number of warps are not enough to hide the latency, and it can lose performance. We evaluated this effect, and we realized that for several applications, we significantly lose performance. For example, in a hotspot, we lose like 50% of the performance, and on average, we lose 13%. But what about the other proposal that is called BOW? In the BOW, we do not use two-level schedulers, but instead, and also we do the caching within the operand collector units, but they assume that we have as many operand collector units as the number of warps in the SM, and there is a huge crossbar between the banks and the operand collector units. They also assume that all the reuses are within a short distance, and they can capture the locality within a small sliding window by storing the source and destinations for all the instructions in that sliding window. When you apply this technique in the subcore-based architecture, it's a little bit more cost-effective because at least now the crossbar is split between the subcores. However, the main problem is supporting tensor cores. Why the tensor cores are the problem? Because tensor core instructions are very spatial. They have large number of sources and destinations, and they result in long reuse distances. By reuse distance, I mean number of executed instructions between two uses of the same value. If we plot the cumulative frequency of reuse distance in two benchmark suites that are called Rodinia and deep bench, we see a huge gap, and always the curve for the deep bench is below Rodinia. And the difference is that deep bench extensively uses tensor instructions, while Rodinia doesn't have any. To capture such long reuse distances, BOW requires a very large register file cache. Driven by these observations, we try to design Memento, and these are our objectives. We try to not increase the number of operand collector units. We try to slightly increase the number of entries in the operand collectors. And instead, we try to increase the effectiveness of policies in issue, operand collection unit allocation, replacement in the cache, and the write policy using the register reuse distances that the compiler provides. By doing this, we minimize the overhead of macroarchitecture. As you can see, we have the same number of operand collector units. We do not increase the size of the crossbar. And even we do not increase the storage in the operand collector units because they already have some buffers to store the operands. And we just propose just adding one bit to show that the reuse is far or near and add some metadata. And by changing the logic in the operand collector, we can make it to operate as a fully set associative cache as well as an operand collector unit. We also assume that each operand collector unit has one port, and the arbiter is modified to decide which values we put in the operand collector units based on the reuse distances. To give you a glimpse of what we mean by optimizing the policies, for example, we changed the issue scheduling policy and applied a new priority for selecting warps. We prioritize the same warp that is scheduled in the last cycle. And why we do that? Because it can reuse the data in the operand collector units and provides the same benefits as GTO scheduler. Then we prioritize the warps that already have data in the operand collectors, since they can reuse the data that is already there. Then we can prioritize the rest of the warps. We also changed the operand collector unit allocation policy. And basically, when we select a warp, we have to allocate one operand collector unit, but we do it smartly because if the operand collector unit already has the data for one warp, we use the same one. And by doing that, we avoid implementing a complex cache coherence protocol. For example, in this case, warp 0 and warp 1 have data in the operand collector units. We just allocate the OCU 0 for the warp 0 that is issued. But what if a new warp is selected and doesn't have any data in the operand collector units? In that case, we have to flush the cache, but we try to not flush a data that has a near reuse distance. So we check that if all the data in the cache is far, we try to replace that first and flush the cache. For example, in this case, warp 2 will be allocated to OCU 0, and we flush the data. However, if all the operand collector units have at least one data that has near reuse distance, we try to even postpone the flushing as long as it doesn't harm the performance. We implement that with a counter and the threshold. If the counter is greater than the threshold or it's equal, we just allocate the operand collector unit and we flush the cache. Yeah, like this example. However, if the counter is less than the threshold, we just increment the counter and postpone flushing the cache. By doing this, we may gain more reuses because, for example, here, let's say we cancel the issue, we postpone the flushing the cache, and in the next cycle, warp 0 becomes ready and reuses the data that is already in the cache. But it's very tricky to set this threshold statically because it's different for different applications, and even in the execution, for different phases, it could be different. So how do we set this threshold to maximize the benefits? Basically, for a short interval of execution, we receive this observation. If we increase the threshold, at the beginning, we gain some IPC that comes out of benefits that we have from reuses. But if we have a very large threshold, we introduce a lot of bubbles, and the IPC significantly drops. So it creates a knee graph, and the optimal point is at the knee point. This is also the optimal point in general because we observed that the graph for the hit ratio is monotonically increasing based on the threshold. So our objective is to that, during runtime, find this optimal point. What we do is that we measure the performance in the current cycle and compare it with the performance in the previous cycle. And we design a state machine that changes the value of the threshold until we converge to the optimal point. When we find this optimal point, we just stop. What was our evaluation methodology? We implemented this scheme in a cycle accurate simulator that is called AcceleSim. We use a configuration of Turing architecture, and for the benchmarks, we use DeepBench as modern deep learning workloads and Rodinia as general purpose applications. For measuring the energy, we use a power model that is implemented in AccelWatch. These are the results that we could gain. For most applications, we gain performance, or the performance is the same. And on average, we gain 6.1% improvement. And the maximum is 28%. And we compare our work against the state of the art that is Bo. And we see very impressive results. On average, we could improve the performance of Bo by 2.9%. And for maximum is like 10.4%. Except two applications, we are better than the Bo. And the worst case is for GEMM that loses 1.7% compared to Bo. We also compared the hit ratio in the cache with Bo. As you can see, for most of the application, the hit ratio that we achieve is much larger. And on average, we have 29% higher hit ratio. We also compared the energy of our scheme with the baseline and the Bo. We could save 28.3% on average for the energy of the register file. And it's much less than the Bo because Bo has like 2.2x higher energy consumption in the register file. In conclusion, Memento is a lightweight register file cache scheme that is designed for GPUs that support subcore-based architectures and also support tensor cores. And we could achieve 6.1% IPC improvement on average, 46.4% hit ratio, and we save 28.3% dynamic energy with a negligible overhead of 0.78%. Thank you so much, and I'm here to answer your questions.
So you're relying on compiler to mark the reuse distance as near or far, right?
Exactly.
So is this completely based on static analysis, or you're making assumptions about like loop
No.
bounds or control flow, anything, or it's just like you're assuming that it's completely known at compile time, the reuse distance?
No, it's very difficult to statically compute the reuse distance for
Sure.
GPUs because we have branch divergences.
Exactly.
And for one reuse, we may have multiple values. What we did a partial profiling,
I see.
computed reuse distance, and use it for the whole
Okay,
execution.
so profile guided. Okay, thank you,
Yes.
thank you.
You're welcome.
So actually, I have one question. So sometimes it's hard to change because the video does not reveal the details about specified caches or something, right? So sometimes I wonder how you actually assume the baseline to specify cache and operand collector operations. Can we make sure that those are close to the sort of the products, like the product of NVIDIA or any GPUs these things?
Yeah, it's very difficult to know that NVIDIA even has operand collector or no, but it's very well known in the academic research that we have operand collectors. But still about NVIDIA implementation, we know that they mark operands with 1 bit, showing the reuse. Still, we don't know that this reuse is about the distance and how they set these bits and how they leverage this bit. Our assumption was that if we implement the cache in the operand collector unit, we avoid many of the overheads that are in the alternative schemes. But still, we don't know that it's very close to NVIDIA or no.
So just assume, okay, this would be the operand collector, so that you just implement your ideas of how that.
Yes, yes.
Okay, if we do not have more questions, so let's thank our speaker again.
Thank you so much.
So our next speaker is Wang, and he's a PhD.
Is the talk number 3 this one or this?
Oh, yes, yes.
This?
His research interests include deep learning, accelerators, and compiler optimizations in high-performance computing, and we influence mental learning. It's interesting. If you can start when you're there.
1 second.
Okay. Okay. Thanks for your introduction. I'm Wang from Zhang University. Today I will talk about analytical tensor architecture modeling and automatic tensor program tuning for spatial accelerators. Tensor computations play a crucial role in various applications, including deep learning and scientific computing. To accelerate tensor computations, hardware specialization has emerged as a potential direction and ushers in a golden age. As one of the recent advancements, spatial accelerators organize a large area of processing elements and a multi-level memory hierarchy. By aligning tensor computations with memory access patterns, they have shown high performance and energy efficiency. They often have strict architectural constraints. We mainly discuss 2 categories, buffer capacity and spatial capacity. These constraints are different on different spatial accelerators. The primary challenge faced by spatial accelerators is tensor mapping. It heavily impacts the computation parallelization with PE area and the data locality in the multi-level memory hierarchy. Tensor mapping divides the target computation into subtasks and scales them on the PE array, where loop optimization, such as tailoring, reordering, and parallelization. This figure gives an example of tensor mapping for gym Simba accelerator. First, the accelerator loads the input and the weight tensor into DRAM and divides them into 64 smaller gems by performs tailoring. And then it loads the subtensors into the global buffer and performs tailoring further. And finally, the accelerator uses its parallel units to compute each gem and write the results to the global buffer. To implement the tensor programs, it is required to complement several tunable parameters such as blue tail factors and red parallel factors. We divide existing solutions into two categories: sequence-guided mappers and template-guided mappers. The sequence-guided mappers define a sequence of decisions to generate complete tensor programs. They require to evaluate incomplete programs, which is either inaccurate or time-consuming. The challenge stays from the step 2. They require to evaluate all candidates of each parameters by alert cost models. However, existing cost models are efficient to the complete programs instead of the incomplete ones. And the number of generated programs increases exponentially with the sequence length. So evaluating so many programs is time-consuming. In general, sequence-guided mappers can't provide comparable performance to the template-guided mappers. The template-guided mappers determine all of the tunable parameters simultaneously. They lead to many invalid programs. This challenge stems from the step 1. For example, the subspace of each tunable parameter influences each other, and they are constrained by the buffer capacity and the spatial capacity. In this figure, C4, after determining C4 as 1, we should update the subspaces of N4 and K4. Choosing values beyond these subspaces, we will get invalid programs. So the template-guided mappers can't accurately constrain the subspace of each parameters. So they often generate many invalid programs. So to address the challenges, we propose Soter. In step 1, Soter constrains the subspace of each tunable parameter. To this end, we design an analytical Tensor-Architecture model to exclude invalid candidates in the design space. Then, in following three steps, Soter makes a sequence of decisions to decide tunable parameters, evaluate complete programs, and performs optimization. So we design an automatic program tuner to avoid evaluating incomplete programs and to generate high-performance solutions. And finally, we built a coordination between analytical modeling and automatic tuning to optimize both tensor programs and program design space. So I'll introduce each design in detail. given the mathematical definition of the target computation, such as Jim, and the targets and the spatial architecture of the target accelerator, such as Simba. The analytical model generates a tensor program design space to satisfy buffer capacity and the spatial capacity. The space is defined with the maximum and minimum values of each parameter. When satisfying buffer capacity, there exist several rules. First, tensors are stored in the multi-level memory hierarchy. For example, the global buffer of Simba or Aries stores input tensor and output tensor. And second, the tensor size can't exceed the buffer capacity. Third, the tensor size is relative to the tailing of each dimension. Finally, we can build a set of inequalities between tail factors and buffer capacity. By solving the resulting inequalities, we can obtain the maximum value of each tail factor. These are some specific resulting inequalities. So our analytical tensor architecture model can be applied to different tensor computations and different spatial architectures by modifying the first and the third rules. Just now, we ensure that the number of tails is enough to satisfy buffer capacity. We also ensure that the number of tails is enough to satisfy spatial capacity. To this end, we can obtain another set of inequalities. So by solving these inequalities, we can obtain maximum and minimum values of other tunable parameters. Given the tensor program design space, we can use the analytical tuner. The analytical tuner performs transformer-based exploration and policy gradient-based optimization to determine all tunable parameters. Each tensor program is described as a sequence. We use the transformer structure due to its robust ability in sequence modeling. So we formulate the program tuning as language generation, and each tensor program is regarded as a language sequence, and the tunable parameters are regarded as language tokens. So the sequence length is a product of the number of buffer levels and the number of tail dimensions. At each position, we determine the parallel factor and the tail factor and the loop order of each tensor dimension at each buffer level. Also, in the coordination, the analytical model generates a tensor program space for the tuner. The tuner explores each tunable parameters within its subspace. The subspace is defined with maximum and minimum values of each parameter. As second, the program tuner makes the model update the subspaces of other parameters through sequential decisions. So with this coordination, we can optimize both tensor programs and its design space. In evaluation, we evaluate our Soter on 3 spatial accelerators, including Aries, Simba, and NVDLA. In benchmarks, we use general matrix multiplication and convolution and so on. And we compare Soter with 4 tensor mapping approaches, including auto-TVM, flex tensor, mind mappings, and CUSA. And Soter achieves, with a batch size of 1, Soter achieves 2.1 to 3.5 times speed up for 3 accelerators across different operators. With a batch size of 16, Soter achieves 2.3 times speed up for NVDLA. And with the batch size, when the batch size increases from 1 to 64, Soter achieves 2.4 to 2.7 times speed up for Simba. And when scaling the IRIS architecture up by 64 times, Soter also achieves 2.1 to 3.3 times speed up. And we also compare Soter with mind mapping. Mind mappings is a gradient descent-based approach for a specific accelerator. Compared with it, Soter achieves 2.9 to 3.8 times speed up. So I'll give a conclusion. We propose an analytical tensor architecture model. It defines a set of inequalities to exclude invalid candidates in the program design space. And then we propose an automatic program tuner. The tuner exploits transformer to avoid evaluating incomplete programs and to generate high-performance solutions. Then finally, we build a coordination between analytical modeling and automatic tuning to optimize both tensor programs and the program design space. Thanks for your attention. That's all.
Any questions from the audience? Okay, if there's no questions, I'll ask one. I see that your Soter actually achieves a lot of performance compared to others, AutoTVM or other baselines, and I wonder what is the source of. Okay, I wonder what is the source of that improvement compared to other sort of the auto tuner, because I think, once you have enough time, the auto TVM or other tuner may just find the final binary or execution files, the mapping basically. So, it's kind of very interesting to see that you get like more than 2x speed up compared to the TVM or other sort of the mapper or auto tuner.
So your question is about the searching time?
No, what is the source of what is the secret sauce of your Soter compared to the auto TVM or other auto mapper or auto tuner?
Oh, okay.
Because you get lots of speed up compared to others.
The reason why our Soter is better than LTVM and Tensor.
Right.
Oh, okay. We say AutoTVM and Flex Tensor are template-guided mappers. So during exploration, they will generate many invalid programs. These invalid programs can significantly decrease the exploration efficiency. Given limited searching time or searching steps, they can't generate high-performance solutions.
So you're using the same number of iterations or steps, because in the end, I think the auto TVM or other actually solution would just find the optimal mapping as well.
So give infinite times. So I think most approaches can find the optimal mapping points.
Okay. So any other questions? Okay. If there's no more questions, then yeah, we can thank our speaker. So our final speaker is Jung Wang, and he's a professor at University of Central Florida, and he has conducted extensive research in the areas of computer systems, architectures, and data-intensive computing. And his research interests include high-performance computing, big data, massive storage and file system, and memory architectures. And he's an IEEE fellow and has served on the editorial board for a number of IEEE and ASIM journals.
Thank you for the session, Chair Jaewoong. Welcome, everybody, and thank you to this session. I'm giving the opportunity to introduce what we have done about accelerating the large language model, which is very popular one program, Inference, well, sparsity-aware KV caching, and this work is done by my student and my colleague, Wu, and they are not able to make this due to the visa issues. So I will present. You know, the AM is very popular, right, without questions, and there's a lot of excited things going on. And inference serving actually is more important. A lot of people doing the training, but only high tech doing this. And for inference, and that's the focus for the academia and other, industry practitioner researchers. And inference serving accounts for most AM-based application scenarios. So how to accelerating this AM inference is the important research problems. And where is the, I cannot, because I want to get the notes. The notes is not, yeah.
I don't know where is the
No, close. They're supposed to have this. I don't know why they cannot read.
Give me one second.
Yeah, it was.
Yes.
Yeah.
Is this one?
Yeah. This final or. Yeah. Okay. Okay, sorry. Okay, and the background is, the transformer is the key. And as from here, the architecture is, the basic building block of AM is the transformers. And it has this multi-headed self-attention module, feed forwarding network, and these, with this layer norm as the connections. And add some layer norm operation with residue connections. The most important component of this transformer is self-attention, this. And the cooperation of the self-attention is shown in this equation, okay? And it will generate 3 vectors QKV and go through a dot product with a softmax operation to produce attention weights. So AW stands for attention weights. And then the attention score is calculated with the product of attention weight and these vector tensors. And what is unique about the LAM is different from the BERT other models is is about these inference procedures. And AM inference usually consists of 2 stages. First is a pre-staging. So AM progress all the input processed at once, deciding a stage where the output will be generated one token by one token, token by tokens. So the second stage is unique in terms of, in order to calculate these, previous, in order to calculate the, previous token, and it has to use the previous tokens QKV WAC tensors to calculate. So that's called the autoregressive inference behavior. This is very unique, different from the BERT other models. And current, like a Google industry solution is using called KV caching to solve this problem and to trying to reduce the computational capacity. And when we calculate the original attention weight, use quadratic complexity. You can look at here. And if we saved the prior KV tensor in HBM GPU memory, then what we only need to do is just compute these new token using the existing old KV tensor saved in the HBM, and which is the linear attention computation capacity, plus and have the KV cache memory access to these old KV tensors. So we KV caching mechanism used very popular today in AM inference is to reduce the quadratic complexity to linear capacities. Well, this is not free lunch, and there's caused a problem. The problem is like the memory issues. GPU memory is limited, right? And this easily will cause the out of memory issues. The reason is the memory footprint of KV tensor is a huge problem. And with the increasing of the total number of parameters, like 1 billion model, you may only have a KV tensor only less than 1 gigabyte. If you talk about 175 billion models, it's going to be greater than 300 gigabytes, which is way more than most of the ones, H100 GPU memories. So memory footprint is a big problem. It's like bottleneck for KV caching mechanisms. And well, we look at the related work. There are some existing work trying to mitigate this problem, like machine learning conference, one flex jam uses CPU DRAM SSD as secondary storage as a backup to save the intermediate KV tensors and model weights. And we AM SOSP 2023 employing the non-continuous page memory mechanism similar to the virtual memory management stuff to save KV tensor as a block level to utilize the GPU memory more efficiently. But these two solutions do not directly improve the KV caching tensors. They don't address the KV caching problem directly. And they also are not able to scale up to the longer sequence, like you talk about the 1K sequence generate token. And other works for accelerating AM inference, all these focus on model weight reduction. They cannot scale to the large AM. And solution need to be work at the whole, from a holistic approach, look at both software, hardware, co-design approach. The main problem is the Fingo 5, get the motivation picture showing, if we use both GPU and CPU memory for AM inference, the time for memory access can even outweigh the actual computation time. So I/O could be the potential problem, and using the DRAM, CPU DRAM, SSD as backup is not the best solution at all the cases. And what our solution is, and how do we deal with this I/O CPU to GPU data transfer stuff? And what motivation we observe is like not all the tokens are created equal. There's some important tokens, some not important tokens. If you look at the large language model, and especially the large models and the token carry very, very different roles. And when you calculate the attention score, attention weights, those are huge difference. And Fingo 6.7, we see the across different steps and layers, attention weight sparsity is very high for different AIM. And the larger the model size, the higher the sparsity. So because of not all the tokens are created equal, there's naturally exists a lot of sparsity when we calculate the attention weights. And the good thing about this high sparsity is that for attention score calculation, if some attention weights are 0, this gives us opportunity just not loading the corresponding KV tensor into the GPU memory. We don't need to say, we don't need to keep them because these attention weights close to 0, right? We don't need to do the calculation. So that can give us opportunity to avoid unnecessary memory access. And here I propose our solution. And we propose a hardware-software co-design approach, and it's an algorithm, system co-design approach. And how do we? The opportunity is like we leverage the sparsity for redesigning the, revamping the whole KV caching mechanism. And one, we identify important tokens is algorithm level. We need a low-cost mechanism to distinguish important token without hurting the AAM performance accuracy, right? Two, we need to design a good sparsity-aware caching policy at system level. When GPU cannot hold all the KV tensors, we need to design a suitable low-overhead caching policy to allocate the KV tensors between CPU and GPU and enforce a low miss rate. Number three, caching and versus recomputation system. And for longer sequences, like the 512 tokens, output token, or even 1024 tokens, the benefits of KV caching may diminish. We need to reconsider how to trade off the recomputation of the partial KV tensors, or instead of just caching in the HBM. And the algorithm design, we develop called sparse window attention, SWA algorithm. We generate both dynamic, static sparse patterns. The dynamic pattern is global and decided using a simple but effective token level local attention weight sum. And the static pattern is local and determined by the recency, just the temporary locality, to keep language generation sequentially. And this is how our SWA attention new algorithm works, and to develop to capture the sparsity and highlight the sparsity, and also without the computer compromising the model's accuracy. And in Fingo, this one there's in Fingo 8 we see compared to the existing solution like static attention model, our method can accurately approximate the original dense attention, while previous static and local methods fail to capture the original patterns. And for the system level, we propose a 3-stage dynamic scheduling strategy, which achieves the optimal trade-off between the caching and RIP computation. First stage, we only use a GPU for storing all the KV tensors. Second phase, when GPU hits the memory limit, we split the KV tensors at the token level and use CPU memory to store the least recent tokens to ensure relatively low GPU cache miss rate. At third stage, we perform recomputation for tensors needed for generation and deleted unwanted KV tensors in CPU memory to maintain the high throughput. And we also employ the additional system. The way we decided the phase change and the caching recomputation ratio is to formulate this problem into optimization problems. And we use a greedy search and runtime profiling to find the local optimal configuration for our scheduling. If you want more detail, you can look at our papers. We also employ additional system optimization, such as KV compressions, that is quantize FP16 KV tensors into the integer 8, reduce the further memory overhead. together, all these three techniques together contribute to our algorithm system co-design solution, ALISA, we call it. And compared with the previous works, our work is among the first to leverage sparsity to co-design the ALM inference. To evaluate the ALISA, we performed experiments on diverse model types and scales, including OBT, Llama, from 7 billion model to 30 billion model size on different data sets across different GPU platforms, including the V100, H100 on single GPU CPU systems. In algorithm results, we can see our system can maintain identical performance as dense attention to up to 80% KV sparsity ratio, significantly outperforming the previous static and local attention methods. In system results, we can also see that our methods can achieve up to 3 times and 1.9 times improvement against the state-of-art FlexGen and VLAM. Our method is especially effective when dealing with the larger batch models, reducing much higher throughput than previous baselines. We also conduct detailed performance analysis for ALISA, like accuracy, in terms of accuracy, whether we downgrade or not, using our SWA. We see that it's a similar sparsity ratio against the full dense attention. On the right figure, we show even our sparse attention methods have some compute underutilization. The overhead is relatively small against the dense attention. To better understand the improved methods against the FlexGen, we have performed breakdown of the ALM. We see these methods makes better use of GPU memory thanks to our dynamic scheduling, policies, and outperforming the FlexGen across different phases and KV sparsity. In conclusion, we want to. Okay. Is automatically cut.
Right.
Okay.
The last slide is just closed.
Oh, I see. Okay. But anyway, yeah, finish my presentation.
This one.
Yeah, thank you for NSF, and my students and colleagues and anonymous reviewers give the comments, and this is the conclusion. Identify a challenge in KV caching for AM inference proposed algorithm system co-design. ALISA. On the algorithm side, we developed the sparse window attention, and on the system side, we designed a 3-phase scheduler. We conduct extensive experiments on both system and the algorithm side. Thank you, everyone.
Hello, I'm Wang Li from Seoul National University, and it was a very interesting talk. And my question is, how does the ALISA identify the missing tokens and decide when to recompute the KV tensors for those missing tokens? Because yeah, that's the first question. And the second question is, how much overhead the recomputation adds to the ALISA? Because I think the time complexity of recomputation of KV tensor might be as similar as the previous stage. So I think it might add some substantial overhead for the ALISA. So how much overhead is it?
Okay, so maybe the question can go to some of my students, but I try to answer. If I'm not able to answer, 100%, you can talk, reach out to my students directly. And I guess the first question is the missing tokens is really the sparsity. So we do the profiling, and they have they capture the global attention and local attention. They have the specific algorithm. And the missing tokens are very likely are the not important token which will not contribute to the calculation of the attention. So which means their corresponding attention weight is close to 0. So for example, in the paper, we use as long as it's less than 1%, less than 1% of the maximum value, like bottom 1%, we treat it close to zero, to zero. So we just mask the, reset the attention way to zero. So all the associated tokens will, be not important. So maybe that's the missing token you think, right? What is your second question?
The time complexity of recomputation.
For our work?
Yeah.
Interesting. Yeah. Time complexity. We don't.
Maybe the third policy is.
Third policy.
Yeah. The third one was. Yeah, caching or recomputation. So. ALISA sometimes recompute the KB tensors, but I think the time complexity might be non-negligible.
Yeah, there is an observation problem, right? This is, there is some decide this offload recomputation something. Yeah, we don't do. I don't think we. Maybe my students do the specific analysis. I don't, but I guess this. We just formulate the observation problem. We don't do the specific calculation on this reduced complexity. As long as we only have the partial KV tensors recomputation, so we don't calculate the whole KV tensors. Of course, we reduce the complexity, right, as compared to the baseline, the existing solution. But to what extent, that's depend on how many tensors we discard, we ignore, yeah. But, you can feel, very, welcome to contact my students, the first author.
Okay, thank you.
Yeah.
Okay, let's thank our speaker again. Okay, so this is the end of session 8B, and then we'll have a break until 4:15. So we only have like 5 minutes left, but there are still posters outside. So if you have more questions, you can actually approach the presenters and say hi and ask some questions. Okay, thanks for your attention. Thank you.